Hello, everyone. I'm gonna, for posterity's sake, give this presentation and record it. Uh, this is a presentation I gave at the Society of Wetland Scientists meeting in Denver, Colorado, the annual meeting in 2018. So the title of the talk is "Don't Wave the River Red Gums Goodbye: The Role of Environmental Flows in Restoring River Water Quality and Riparian Zones Along the Wimmera River." Before I really kick off, I really want to thank Greg Fletcher. He's been a great colleague and co-author on this presentation and this work. He really put me on the scent of this work, kind of directing me to some outstanding resources, and I kind of took it from there. Again, before really jumping into things, this work wouldn't have been possible without the sharing of data through these various state and governmental agencies, including the Environmental Protection Authority of Victoria, especially Anne Marie Westbury and her staff, the Australian Government Bureau of Meteorology, as well as the state government, the Victoria State Government Department of Environmental Land, Water, and Planning. All this data is publicly available and was mined just to specifically ask and answer some questions along the Wimmera River. So before really jumping into things, I really want to kind of highlight this. So being ecologists, we have a duty to both look at the wildlife, the aquatic ecology, the ecology of the system, but also the ecology of the system relative to the human dynamic. This presentation's title was inspired by a John Williamson song, Salisbury Street. And in the lyrics, it says, "Don't wave the river red gums goodbye. Just thank her for the shade and the stories." Granted, this song isn't specifically about river red gums, but it does kind of highlight the importance of this species. And also, John Williamson, for us Americans, he's analogous to John Denver. So he's like an Australian John Denver. For you Aussies out there, he's probably, John Denver is probably the American John Williamson. That being said, you guys can do the homework and kind of report back if you really want to. But if you take several of John Williamson's songs and take his lyrics and kind of export that out and put it into a word cloud, or in this case, a word water droplet, you can see that river or water is highlighted a lot in his music, as well as some of the iconic rivers and watercourses in Australia, including the Murray, the Snowy, Hawkesbury, but also areas such as Longreach. So in this sense, Australians, and for the most part, lots of other people, water and rivers are very important features on the landscape, both ecologically, but also culturally. Kind of wanted to bring that out before we really get into the science of things. So real quick, floodplain 101. Not everyone's a floodplain ecologist or biologist by any means. So this is a cross-section of the floodplain. You can see on either end of the channel there. Let's see if I can do this. The channels here. You have the riparian zones on either side, which are the floodplain. And eventually there's a change in elevation and you get a terrace. Now the below ground stuff, there's a lot of stuff going on. It's just not water on the land with some trees and sloughs and whatnot. There's some exchange between groundwater, the water table, the sediments going into the river. So floodplains, much like wetlands, are ecotone ecosystems. They sit between the terrestrial and aquatic environments. And they're very dynamic. There are dynamics, especially spatially, and they're shaped by water. And they transport large fluxes of energy in the form of physical energy of moving of water, but also chemical energy in the sense of nutrients and sediments and material from upstream. Here's a cross-section, another cross-section of a floodplain showing the importance of water level and its influence on vegetation distribution. This is specifically a cross-section of Australian floodplain. So you have the river red gum forest right on the edge, transitioning all the way up to a black box woodland. And the durations and the frequency of flooding really matter. And you can see from these dashed lines, you have max, high, low, and banked full flooding. Now, if you take that step one more step further, you have this idea of flood pulse regimes, and they're extremely major controlling factors in the floodplain ecosystem. And that, as the water is low in the low season or the dry season, eventually rains come, and you have this flooding effect where the water comes up the floodplain, hydrates some of that higher area, and if the water stays for long enough, you start facilitating some emergent aquatic vegetation and submergent, and then eventually it all draws back, and that emergent vegetation kind of dies back and gets incorporated into the soil as organic matter. Here's another cartoon cross-section of kind of the various factors that influence surface water salinity in specifically Australian dryland agricultural areas. This concept could also be extended to the areas in Western America where we have large-scale salinity or salinization of surface water and sediments as well. The ones that I really want to highlight here are the removal of native vegetation, which kind of changes the groundwater regime a little bit. And in doing that, the water table rises and mobilizes some of the minerals in those soils, which results in saline soils, but also saline surface waters as well. Here's another kind of cross-sectional area to kind of get at the different processes of formation and mixing of saline pools in river systems specifically. So you have essentially, during low flow, the water level is really low, and you have this potential for groundwater to seep into the stream. And now if that groundwater just so happens to be in an area where it's saline or where it's relic deep groundwater is seeping up, then you can have the potential of groundwater discharge into the river there. Now, alternatively, during high flow or when the river is staged up, you have this freshwater flow that's pushing. For the most part, it's going to go over top of the saline water because of density gradients. But you're going to have some of that as it's getting put, as the fresh water is coming along, it's going to push some of that saline water downstream. So our study area specifically, the Wimmera River originates in the Grampian Ranges, very beautiful scenery up here. I mean, I would love to hang out on that cliff for a little bit. And it ultimately terminates in Lake Hindmarsh. Here's a map of the lower portion of the Wimmera River, where if you see this little red dot here, this is Horsham down in that area. It jogs west a little bit and then eventually turns north and terminates here in Lake Hindmarsh. This Wimmera Basin covers approximately 10% of Victoria, so this yellow area here in this graphic is kind of the basin relative to the state of Victoria. And approximately 85% of the native vegetation was cleared for agricultural production, such as wheat and some of the other grain crops. Here's a real quick snapshot of the aerial imagery of the Wimmera River Basin or Wimmera River floodplain. Here you can see it kind of cutting diagonally across the image near Dimbula, and I apologize if I screw up any of these names. So this image was taken in March 2017. Now, if we go back in time, we have January 2011 when a really big flood impacted the Wimmera River area, especially the area around Horsham, Dimbula, obviously. You can see here for comparison, this highlighted area is a grain storage area, so it kind of gets you some perspective. The next little piece of land on the landscape, you can see this area here. You can see in 2017, that's a relatively dry, isolated wetland. In 2011, it was completely flooded. And this red line kind of delineates, at least in the 2011 image, where the flood kind of extended. And in 2017, you can see that it's dry agricultural lands for the most part. You can see that there's also changes in elevation across that floodplain given the inundations. Here's another kind of aerial image. It's shot out the side of an aircraft or a helicopter. You can see that this grain silo area here, you can see the river red gums, and you can see the road cutting through. Another image you can see is kind of in this general vicinity on this image here, kind of showing another oblique aerial of agricultural lands impacted by the flood, but you can also see the floodplain as well. So effectively what we've done, or what the Wimmera River basin looks like, is this. It's the, remember this image from before where you can see the transition from river red gums all the way to black box woodlands. The mid to upper areas of the floodplain are actually, the vegetation is cleared and you have agricultural lands there, or maybe even cities or towns. So real quick, want to have you guys devote this to memory. Just kidding. So these are flow sites, or sites that measure discharge and water level along the Wimmera River and within our study area. And so we have sites, or there are sites from Wimmera, Horsham, however you want to delineate that, all the way up to Hindmarsh. And you have Mackenzie Creek and the lower Norton Creek kind of feeding into the Wimmera River. They're very small tributaries that feed into it. Now remember these sites, you can see here's a hydrograph of annual discharge volume at these various sites. The Wimmera site has the longest period of record. Here I only focused from 1920 to 2017, I believe. But the period record reached back all the way to 1880s, I believe. And so you can also see there's other sites that come online eventually, Mackenzie, Norton, Dimbula, Terranurk, and Hindmarsh. You can see that as you kind of move, the units of measure kind of change a little bit. You can see that Norton and Mackenzie aren't really, Mackenzie's a bigger contributor than Norton. And you can see that as you get further up to Hindmarsh, there's very little discharge out of Hindmarsh, from the lake to further downstream. And you can also look at this in a cumulative fashion. So starting in 1920, the cumulative annual flow or discharge versus the cumulative rainfall within the basin. And you can see the line is very jagged and is not like a straight line straight up and to the right. And this jaggedness relates to changes in rainfall and runoff patterns. And so in a period of a drought, for instance, we would have very little rainfall, so it would kind of tick along slowly, and very little flow. But when we have flood season or flood years, the slope of that ultimately changes. And if you kind of try to pick out the dots, you can see it picks up the World War II drought as well as the millennial drought and several others in between. You can also do that for other stations. Granted, these Terranurk, Lochiel, and Dimbula, again, I'm sorry if I screw up the names a little bit, but you can see that this relationship sticks, but it varies along the way. Each basin receives a little bit different rainfall patterns, as well as a very different discharge. You can see that in Terranurk, especially the millennial drought, really impacted that site very, very heavily. So now moving on to salinity or specific conductance. So in this plot to the right, you can see there's specific conductance in the gray, and the red line there is water level at these sites from Horsham to Terranurk. And one thing to note, the specific conductance units are in microsiemens per centimeter. Now, for you freshwater folks, we typically measure in microsiemens. A couple hundred to 1,000 microsiemens is fresh water. For you marine folks, this Terranurk site, for instance, at 60 millisiemens per centimeter, that is probably equivalent to about a salinity of 2 to 5. I can't remember the calculation off the top of my head, parts per thousand. So it's a low salinity in the marine sense, but a very high salinity in the freshwater sense. You can see if you kind of tilt your head a little bit and you look at it and squint your eyes, you can see that as water levels go up, your salinity drops. And conversely, salinity goes up when water levels drop. And this is most exaggerated in Terranurk, and not so much in Horsham. Horsham's almost a semi-normal freshwater site. And so there's this correlation between water level and conductivity, specific conductivity. And there are obvious hotspots of salinity along the river. So one thing we could do is we can look at macroinvertebrates or water bugs. Water bugs are really great at telling us the condition of the ecosystem. And so here's a couple of examples of water bugs that I pulled from the mdfrc.org site. And there's specific indicators for each taxa, each species. And so we can leverage that data, and there's different tolerance or sensitivities to both nutrients, flow, salinity, especially. And so we can have this salinity sensitivity index. And this is the equation that it calculates. This salt salinity sensitivity score is ultimately what drives this. And that score can be found in this reference here if you're really curious about all of that. And so ultimately what this SSI metric tells us is if it's a value of 1, it's relatively salt tolerant species. If it's a value of 10, they're very sensitive to any salinity. So ultimately you have a freshwater water bug, for instance, if you get a value of 10, if you have a value of 1, you have a species that's really resilient and can kind of hang around in any condition. So if you take that, crunch the numbers, you can calculate that salinity sensitivity index across our study area here, and correlate that with specific conductance. And there's a very strong negative correlation. So as salinity goes up, your sensitivity index goes down, and vice versa. Yeah, you can also look at diversity in the sense of the Shannon diversity index here versus salinity sensitivity index. And you can see it's a kind of a flipped relationship where you have a strong positive correlation. So as your salinity sensitivity index goes down, you have lower diversity. So you're specializing your community because of those drivers. And then also salinity is a lot higher, or diversity is a lot higher if you have higher salinity sensitivity index, especially for the Wimmera River. As I said, the periods of high salinity within the river has influenced macroinvertebrate water bug, as I like to call them, diversity. And as expected, you have this opportunistic taxa, the less saline sensitive, were present at both impacted and unimpacted sites, while the higher salinity sites correspond to a lower diversity and have the more resilient species to it. And this analysis specifically gave me a better or greater appreciation for these macroinvertebrates and kind of what they're telling the story of the river. So we can take another look at this in a synoptic fashion. Instead of looking at any specific site along the river, we can look at a group of sites along a particular river reach. And so we have 5 river reaches here. And this SSI index was calculated for each reach and for each site within that reach. And we compared them along the reach here. You can see that the lower reaches here, or the upper reaches of the lower Wimmera, that's not confusing at all, are actually, relatively, they're alike, as you can see in this plot here, where you have Kwantong, and I apologize again if I completely murdered that, being similar to Horsham, Norton, and Mackenzie stretches. Dimbula is different than that. Loch Shiel is different than that. And then you have Chaparrot, and Terranure, who are the obvious kind of completely different from all the others. One of these things is obviously not like the others. And now if you take that, and I'm going to totally geek out on you guys, in a kind of a multi-dimensional space, looking at not only just conductivity, this SPC here, but also temperature, DO, pH, versus the salinity index and diversity here. You can see that specific conductivity is kind of stretched all the way out to this side, indicating that that's a strong driver for this particular group of sites. Now, granted, this plot is very abstract to understand or interpret, So another cleaner way to do it is do it with ellipses. And so you can see here that Chaparrot really kind of breaks out from all the others. And I apologize, my voice is cracking. So I'd be remiss if I didn't bring up river red gums, since it's in the title of the talk. So here is a time series of diameter breast height, or DBH, for river red gums. Along the river, looking at those same stretches, those same regions. And you can see that Horsham, Norton, and McKenzie have seen this interesting increase in DBH up to about 2011. Then after 2011, it drops down. And this so happens to correlate or correspond to the big flood event in 2011. So where I'm sure that huge flood event in that region really impacted the river red gums, causing a lot of the older trees to die off, leaving the smaller ones. As you move downstream, the diameter breast height kind of decreases as you move down, as shown in this plot. And you can see that the lower reaches here, so especially in Jeparit and Alexio here, stay relatively constant throughout this time series. And not data that's presented here, but in this report here by Carr, 2015, there's another metric called general canopy health. And you can see that the data that they presented shows severe impacts downstream, especially in Jeparit and Alexio, especially in the areas where salinity have really been high due to drought and low flows. And so ultimately, the environmental flow program has been kind of implemented, and we're seeing steady increases or improvements to some extent in this most recent data collection for some sites, but not all. So it's not a complete fix. And ultimately, so as we wrap this up a little bit, so the discharge volume is highly variable from year to year. If you guys remember the annual hydrograph for Walmer or Horsham, you see that there are very big boom and bust periods of flow. And, you know, it's evident in the millennial drought where you guys had 9 to 10 years of no or minimal rainfall to in 2011, there's a massive flood. And along this river, there's specific conductance varies pretty much from north to south, with notable hotspots which correlate with water level, especially near Terranure and Jeparit. That macroinvertebrate diversity and salinity index, or salinity sensitivity index, given that there's changes or hotspots in salinity, varies along the river dramatically. And also to correlate with that, the river red gum canopy health is significantly impacted along that, along the river, especially at the lower reaches where we see these salinity events. And so there's been engineering solutions to kind of consider to reduce the occurrence of high salinity waters in these hotspots. Granted, it's a significant monetary investment, but you know, there's discussions about it at least. Also, you know, there was a pipeline that was put in from the adjacent watershed to be able to bring water into the river to be able to meet those environmental flow targets. And so all in all, the river has gone from impacted with salinity hotspots. Granted, it's not completely fixed, but there's momentum to improve the river. There's not presented here, but in other studies, there's been improvements in fish species occurrence and abundance along the river. There's been community engagement, which has been a big thing, where the community comes out and is involved in plantings and involved with the environment of the Wimmera River, which is great. So with that, granted, you guys can't ask me questions directly, but you can put questions in the comment box. Since this is going to be posted to YouTube, YouTube universe, or you can shoot me an email at pjulian@ufl.edu, or you can follow me on Twitter, Swamp Thing Paul. So thank you very much for listening to this presentation. And again, if you have questions or want to add to anything, feel free to drop me a line. Thank you very much.